Well, good morning again, and welcome to our webinar with Viavi on the 5G air interface, especially concerning C-band. My name is Steve Case, and I'm the moderator today, and we'll be getting started right now. So with that, today we have from Viavi, we have Eduardo Inzunza, and Eduardo's been with Viavi for 9 years and 25 years in the telecom business, and bringing a lot of experience to the table here for us today. And I've been in the industry a little while. I've been with Electro for 8 years, and largely in product group supporting RF, microwave, telecom, and some other product segments. So good morning, Eduardo.
Hey, Steve, good morning.
So we just have a couple of things to go over before we get started. We have a little commercial about Electro, of course. And we're a large test and measurement company with a large inventory. I think it's $1.2 billion now, with lots of locations and employees all over the world. Most of our assets are located in the US, in California, and in London, with assets also in Penang in Asia and in Beijing. So no matter where you are, we can cover you with Viavi equipment, whether it be data communications equipment, OTDRs, spectrum analyzers for 5G, like we're talking about today, and lots of other equipment. So actually, before we get rolling, we will have the ability to take your questions. There's a questions and answers section in the GoToWebinar section that we have there. I'll be monitoring that. And then Eduardo will come to me and see if we have any questions going on. And please do that. And I think with that, Eduardo, I'm going to change it over to you and let you get started here.
Okay. So
take it
hello
away.
again. Yep, thank you. Hello again, everyone. And as Steve mentioned, we're going to be talking about 5G air interface. In this session, I'm going to be talking about just kind of the introduction of 5G in mid-band. And later on, we're going to be talking about specifically on things about interference or some impairments that might happen in 5G mid-band. And then I'm going to be closing out with some resources. Along the way, I'm going to be making some pauses just to see if you have any questions. So feel free to post your questions and we'll try to answer them. So let me start with the key technology elements that exist in 5G as enablers. And among all of them, perhaps the most important one is spectrum, new spectrum being available. And for that, we've seen different companies kind of participating in these new spectrum. For example, the big operators here a couple of years ago, 3 years ago, they actually participated on a new spectrum being available, and that's a millimeter wave. The other ones basically move into 5G, deploying it in lower bands. So we've seen some 5G in, let's say, 600 megahertz. Some other deployments that we have seen. I apologize. Give me just a second. So some other operators deploying it in DSS, for example, and that's basically sharing the spectrum they have available in LTE and making a 5G coexisting with LTE. And the main goal, the main purpose was coverage. So the deployment of 5G in those bands, in the, let me call it low band, that's the main purpose was one, to deploy 5G, although not necessarily for any significant improvement in service or mobility, but more just to provide coverage and 5G being available. But bandwidth, in all honesty, was pretty much the same as LTE. As we all know, the signal format of 5G is basically the same as LTE. Now, the main aspect, I apologize, my timing is not quite right here, but I just want to point out that the main aspect for 5G mid-band is that the goal is to cover both. or to have both characteristics, the characteristic of coverage as well as capacity, because in capacity, now the operators will have new spectrum available. They're not going to be using or refarming, let's say, the LTE spectrum they have now, but new spectrum is available. And with that, actually, one of the key components of it is the ability to have more channels that are wider. So in the previous spectrum, the allocation was driven primarily by the LTE channels. Those were 20 megahertz wide, and even though they can aggregate multiple channels, in 5G midband, they are going to be able to do it with wider channels, as wide as 100 megahertz. So a lot of improvements or efficiencies, certainly, with midband. So let me just give you a picture of how this looks and some of the other characteristics that exist in each of these bands. So I'm going to start with the millimeter wave. And here we have big channels. This is just one example. Channels can be wider. According to the standard, can be all the way up to 400 megahertz. But the deployments we've seen, and this is an example of one of those signals, is 100 megahertz. And one of the things that we've seen in the millimeter wave, and these, I'm just giving you an example of the problems or challenges of millimeter wave, and that's related to the free space path loss, or the loss that it has at that frequency, as we can see here in this example, according to just relationship that exists on the path loss and distance. Just in a mile, the loss or attenuation is going to go down to 125 dBs. So certainly that drives the need of a lot of different sites, a lot of different density on the sites. So the other aspect that I want to point out here is the loss that exists in these signals, how sensitive they are for, in terms of materials. This is a table that I have here on the right-hand side. As we can see, we have a lot of different problems if we want to penetrate buildings that are built with concrete. As you can see here, with concrete materials, basically no signal goes through it. As we can see here on this table, we have a loss of 117 dBs. So certainly a lot of different challenges for millimeter wave, despite the fact that we have a lot of capacity. Coverage is a challenge. Now, moving along with the next example that I have here, this is for the low bands. And even here, as this example, this is just the 5G channel. I open it up into a wider channel or wider bandwidth, if you will. But here, as you can see, the channel that we have is just 10 megahertz. And we've seen these very typical of just using low frequencies. However, the channels are narrower. So in this example, if we just take a look into the characteristics of how far the signal can go and how well it can go through materials, we see here that in these low frequencies, the attenuation is not that severe in terms of just pure free space path loss. For the same mile in distance, it's 92 dBs in comparison with the previous example that I had of 125. So that's more than 30 dBs kind of in comparison. And the other aspect that I want to point out as well is in terms of materials that is not as severe. In the case of midband, though, this is an example of midband. And as we can see here, we can have channels, and this is one of the deployments that we've seen. It's up to 60 megahertz. And in 60 megahertz, again, as a comparison with the other bands, in LTE, the maximum bandwidth was 20, and they can aggregate multiple carriers. In the case of 5G, a single carrier can be 60. So again, a lot of efficiencies can be achieved with 5G, kind of not a lot of overhead for aggregating, but a single channel can be as wide as 60. And the other characteristics in terms of the free space path loss and penetration, very good characteristics all around. I mean, even though there's some challenges, and again, with the example that I have in the distance of a mile, it's about 108 dBs. But that's just physics, and I believe certainly all the operators are planning the network accordingly to provide full coverage. They're allocating a lot of these 5G mid-band sites in the LTE and adding more sites to provide full coverage. And then in terms of the profile of materials, as we can see, it's very acceptable. Let me call it that way. Again, depending on the different materials, the most severe now we've seen that it's a mix between the reflective glasses in buildings or concrete, but again, pretty acceptable to penetrate those materials. Now, that was just in terms of how wide the channels are and some of the efficiencies. However, the other aspect that we're seeing now with mid-band is that 3GPP has defined these bands. So when we call mid-band, that basically is between 3.3 and 4.2 megahertz. So one of the characteristics is that it's TDD based. So TDD means that it's a time division duplex mode. What that really means in comparison with what we've seen in LTE, primarily in the low bands, is that in LTE we had the uplink and downlink in different frequencies. And just for everybody's clarification, uplink is the signal that is being transmitted by the mobile, and downlink is a signal transmitted by the radio. So different frequencies. So it was kind of simple to assess for any interference problems that typically happens with the uplink. In the case of mid-band, however, both the radio and the UEs are going to be transmitting on the same frequency. And they're going to be able to do that because they're going to be having specific timing or time slots from which they're going to be able to transmit signal. Otherwise, the signals will collide and no communication can be established. So the way in which they're deploying it, and I just put kind of a table down here below, is basically the time allocation based on symbols of downlinks and uplinks. So different operators are going to be able to make this configuration, and it's important that actually for this signal format, it's going to be the same nationwide. Otherwise, there's going to be some problems that some cells will be interfering because the downlink slots might be on top of the uplink. So in essence, some of the radios might be interfering with mobiles. But in any case, this is just a pictorial here on the right where we have on the same frequency is just a time allocation between downlink and uplink. Okay, so this is just an introduction. Next, I'm going to be talking about interference analysis. Now, actually, before I continue, let me just pause for a second and see if there are any questions so far.
No, there's no particular questions about the topics yet.
Okay.
People are wondering about mics. All mics are muted in the webinar, so it's just myself and Eduardo. So, but that's the only question. Go ahead, Eduardo.
Okay. Okay, so now that we have just a broad idea of the signals in 5G, specifically high band, mid band, and low band, and these unique characteristic that all 5G signals in mid band are TDD based, let me just go into some of the interference and how we can analyze interferences in mid band. So overall, the concept of interference typically is because some other devices might be transmitting on the same frequency as in 5G midband. So we have the downlink. Again, it's the signal transmitted by the radio, high power. It's anywhere from 43 to even higher. And we have the uplink. The uplink is the signal transmitted by the mobile. And as we can see here, the mobile have a limit in terms of signal power, and that it's a maximum of 23 dBm. So certainly, if we have a device that it's interfering with this frequency, is going to affect primarily the uplink or the mobile. Why? Because it's going to be competing against a low power of the mobiles. So that's typically where most of the problems happens. Typically, the downlink kind of overcomes that interference signal, but not so the mobiles. So typically, we kind of look into the spectrum and see for interferences. And here it's an example of an uplink interference. Here, it's just a spectrum. In this specific example, a real-time spectrogram in which we capture the activity of the uplink, and as we can see, we had an interferer. Now, these interferences might happen because of external or internal sources. External, so can be any device that I have seen some IoT devices or some of the utilities devices that actually the oscillator went off and happened to be transmitting on the same frequency as the uplink. Or some broadband amplifiers and video cameras that I've seen some every once in a while that are interfering with the mobiles. But also can be internal sources. And those internal sources can be just harmonics or spurious or even passive intermodulation or PIM that is created by the same cell site. Or even, and I have an example later on, that we might have interferences between cell sites, but I'll explain that a little later. So how to assess for interference? Typically, we've seen that overall it exists some key performance indicators from the management system. So we see that there's a problem in the network. Now, to solve it, then we have to do an interference analysis. And for that, the first step on interference analysis is to have an interference profile. So understanding what is the behavior or the profile of the interference. And it can be done in a couple of different ways. One is connecting directly into the fiber link and then assessing how the uplink signal looks like. And again, just kind of looking into the interference and see how it behaves. Or making an over-the-air test and basically looking into the spectrum and see how the interference behaves. With that profile, then we do interference hunting. Basically, that is the to locate where that interference is coming from. So once we have defined the area, then we have to identify the source or the device that is generating that interference signal. And with that, typically at the end, then we just close it out with some mitigating or removing that device that was oscillating or interfering, and then create reports. Typically, that's how it's done. So I'm going to spend a little bit of time here as an example of different type of interferences. We have grouped them into three main categories. One is a wideband interferer. This is an example. I think this actually happened on a cable TV that was leaking. As you can see here, it was about 6 megahertz. So this is an example of a interferer. And a different type of interferences are the narrow band interference that basically are narrow and always exist. And the third type are the interferences that are changing in frequency. We call them frequency hopping. So those are the 3 main groups or categories. Now, to assess the interference, as I said, it's the ability to characterize that interference. And typically for that, we use the spectrogram. Here, the spectrogram is where you're going to be able to see basically the spectrum, but also the signature across time as a waterfall. And that's going to help us to have a good sense of the interference and how, if the interference is constant or if the interference is fluctuating. So here we have changed from downlink to uplink, and we will see now across time if we have an interference. And here we happen to have an interference, and we've seen these with some industrial machinery, some welding machines that every once in a while they just come up, and we see interference that is predictable. It has the same pattern, but it's on and off. So certainly the spectrogram is a good way to characterize the interferers. So going back to my concept of the different transmission modes, typically that was easily done. Again, because in the low bands, we used to have or been transmitted in FDD or frequency division duplex. So again, we can just look into the spectrum of the uplink without any problems. And that's because, as I mentioned before, we have the uplink in a different frequency than the downlink. Now, in time division duplex, and yet again, all the 5G signals in C-band are going to be TDD. And here again, the challenge is that we have the same frequency, it's going to be downlink and uplink. So here we have the challenge of how we're going to be able to assess the profile of the interferer without looking into the downlink, because the downlink basically is going to mask any interference that might be in the same frequency. So here the objective is just to trigger our analysis on the uplink time slots. And for that, let me just elaborate a little bit more, give you an example of how the TDD is being allocated. So we have first the signal itself on the left-hand side. And again, it can be all the way up to 400 megahertz. In the case of C-band, it's going to be up to 100 meg. And then on the, if we look into the time, a 5G signal has a frame of 10 milliseconds. And then, as you can see, it's partitioned in different slots. And the mobile operators can basically define what's going to be the configuration of each of those slots. In this case, I have a configuration of 0032 and so on. Basically, what that really means is, again, where the downlink and uplink will be allocated on a 5G frame. So we have downlink, flexible, and uplink. And the flexible basically is being in between downlink and uplink. It's just the guard period of that transition. So the other aspect that we've seen in terms of deployments in 5G, and this is 5G in general, is non-standalone versus standalone. And I'm just gonna make this comment because in what we have seen as non-standalone, which has been most of the deployments now, that basically means that the mobile has two connections, dual connectivity. Let me call it that way. So that connectivity is with LTE and 5G. And here the notion is that in LTE is going to receive all the signals of control. So all the establish connectivity with the 5G and all the control in terms of signal strength and so on is going to be over LTE, but data is going to be over 5G. In comparison with 5G standalone, which both data and control are over the 5G signal. And by the way, this can be the same signal or can be different signals, but in this example that I'm showing, we can have, for example, 5G control in mid-band and 5G capacitor data, if available, in millimeter wave. So still dual connectivity, but all the control signaling, it's over 5G. Now, I'm going to go back into that concept of NSA and SA and what's the benefit of it. Let me just stay with non-standalone. So non-standalone, again, all the control signal is being delivered via LTE. So how we can assess of interferences without the control signal. And with that, we basically do a gated sweep. So we gated the spectrum into the uplink time slots. That's the goal. So here we have that functionality. Basically, we have on the top of my screen, we have the time domain. So we can see in one frame where the downlink and uplink slots are. And here we can actually have the ability to look into both uplink time slots. So we have a couple of gates in which we can trigger the spectrum. That is going to give us the visibility of the spectrum down below, which is frequency domain. That's the spectrum itself. And as here as we can see, we have clear visibility of the interference. And again, just as a comparison, on the left-hand side where we have just a pure spectrum analysis, this is just spectrum across the entire time. It's not that easy to see if we have an interference. However, if we have, again, the ability to trigger the spectrum just on the uplink, we are basically looking just on the uplink traffic and interference. And as here we can see, it's very clear that we can identify that. And even more so if, again, we have the ability to have two different gates. So we assess the interference in both instances. So let me just now give you an example of NSA, and actually here is a 5G signal in midband. So we have the time domain here. We have 5G frames, so we're looking into a 10 millisecond signal. And here, as we can see, we have the uplink in two different time slots. We have a couple of gates that actually I put there. And then in frequency domain, we are now looking to 60 megahertz, which is the channel width. And as you can see, there's a little bit of traffic, but also we can see the interferer right there very clearly. So that's a methodology, and very quickly, as you noticed, that's the way to assess for interferences in midband. Now, the other aspect is what happens in 5G on standalone. So in standalone, we have, again, the connectivity between the radio and the mobile, TDD. So that's a mix of uplink and downlink. So here we have the different formats that, again, operators make. And one of the things that we have developed is the ability to automatically assess of those locations or those time slots where the uplink is being transmitted. And we can certainly do so by first analyzing the signal, and then with that information that is being transmitted over the control signal. So again, let me just make the point that here in the standalone, the control signal is available in 5G. Therefore, we can grab the entire the 5G signal and assess via all the MIB-SIB data or the control signal being transmitted in 5G, and assess how is the downlink control information. In other words, where is the uplink time slots? And that's basically how we're going to be able to trigger automatically the spectrum, just to assess for interferences. And we call this capability the 5G tags, or TDD aggregator spectrum. So this is something that it's new, so we are going to be able to easily assess for interferences in 5G standalone. Now, once we actually, before I continue, let me just pause for a second. Probably I went a little too fast, and let me see if we have any questions.
We don't have any questions from the audience yet, but I was curious about the TDD interference that we see. Is this caused by the PTP timing misalignment?
Oh, good question. And the answer is yes. And I do have an example a little bit later that actually I'm going to elaborate a little bit more on what is the impairments or problems that we can see in terms of synchronization problems, and will that incur into some sort of interferences between cell sites? The answer is yes, but I'll explain it, or I'll elaborate.
Okay, great. I must have missed that when I looked at your slides. Okay, go ahead, Eduardo. Thank you.
Okay, no worries. So yeah, feel free to ask any questions along the way, and we'll try to answer them. So now that we have an understanding of how the interference behaves, the next step is to hunt for that interference. And typically we see here a couple of different ways of doing so. One is what we call the spectrum clearance. So that's before the cell sites are transmitting. Here the notion is to make sure that the spectrum is clear. Or once the radios are being commissioned and deployed, then we do an interference hunting. So let me just give you a couple of examples. And typically either of these tests are being done in a drive test manner. So automatically we just use a little bit of software and an antenna that connects into the instrument just to easily do a drive test and locate the interference. So I'm going to start with the spectrum clearance. So here, again, the goal is to assess that there are no interferers in the C-band. And in a recent test that I did, I happened to find an interferer that was transmitting on the C-band that shouldn't be. But here, the way in which the instrument works is that, again, just in a drive test, everything should be quiet. Everything should be in just the way in which we present the heat map. Everything should be cold or low power. In places where we have signal present, we have a pass-fail notation, and that's basically with some circles around those data points, in addition to the signal strength being with a different color scheme in each of the measurements. And we collect in each one of them the spectrum. So as here we can see later on, we just select the data point, and we can see where or how the spectrum the spectrum signature is on each data point. And here just don't know if it's clear, but we can define a power limit. And if the signal goes above that power limit, that's our pass-fail trigger. So again, very easily we can assess if this spectrum is clear on the intended area of coverage. So that's one. This is, again, just a spectrum clearance perspective. Now for interference hunting, here I have an example that I did where the notion here for interference hunting is we're going to be able to get a similar heat map, but here we're looking not at the entire spectrum, but we're looking for that interference that we have the profile of we have characterized. So we're going to be making measurements on the interference to assess the the area from which the interference has the highest power. And automatically, while we're driving, the solution is going to give us the suspected area of where the interferer is. And then along the way, it's going to be collecting more data and making automatically zooming down into the area where the interferer is located. And then at the end, we're going to be able to get some driving directions that is going to basically send us back to that area where the location where the interferer was the strongest level. Here's the example that I have. So this is an actual test that I did of a real signal that I found with this solution. We call it Eagle Eye or Interference Advisor. As you can see, the option that I have is for interference hunting. I just make a connection from the solution to the instrument. In this case, I was using one advisor. Here, I noticed that interferer, and I select the tracking mode as channel power because it's a wide signal, and that was it. I would just start driving. So on the driving, I didn't do anything until the end. So automatically, again, the solution is collecting data, collecting measurements of the signal strength, and based upon those data being collected, actually draw lines of the area where the signal was the strongest through the route. So at the end, basically, well, as you can see here on the right-hand side, I see the spectrum. We've automatically found the place where we had that problem. The end was just able to just stop then and assess where the signal is, and the solution gave me directions back to that location, and I was able also to create a report. So in this case, it was interference in 700 megahertz, and it just happens to be a government entity that was leaking a little bit of signal in this frequency. But this is just an example on how easy is to find interferences, even though this case or this example was in 700. Similarly, can be done in midband because we can just select the solution to do this type of test with gated sweep. And again, that gated sweep or gated spectrum is the methodology that we'll be using to assess interferences in midband. Now, once we have found the location, the next step is to find the device that is sending that signal. And again, those devices can vary and can be some, again, IoT devices that just go crazy, or can be some broadband amplifiers, or can be some video cameras. So again, a lot of different possible transmitters. For that, we typically do a walk test now, and in that walk test, we use a directional antenna that in that walk, then we're going to be able to assess or find that transmitter. Now, in terms of the question that was well, before I continue, let me just pause again and see if you have any questions.
No, we don't. Not at this time.
Okay. Okay. So in terms of timing, synchronization, and if we have any problems with synchronization and what those problems might be. Actually, for that whole concept of synchronization, 3GPP has defined something that is called the cell phase synchronization accuracy. And to be specific, this is certainly applicable for TDD signals. And it states that the maximum deviation that exists between two cell sites should be lower than 3 microseconds. So what that really means is that, well, first, we do understand that both cells are transmitting the same configuration of downlink and uplink. right? So the signal will not collide, although that makes the assumption that both have the same timing. Now, if there's a time problem in either of these cell sites, we're going to see that there might be a shift or an offset in time, and then that basically will be that the downlink that will be on top or overlapping on the uplink slot, and that certainly will be a problem, again, because the downlink will be interfering with the uplink. So the way in which now we have the ability to test these and ensure that there's no problems is through this test or this metric that 3GPP has defined, which is called cell phase sync. Here on the right-hand side, I have an example of this. These 3 microseconds, it's basically on the top of the screenshot that I have there. I have 3 microseconds plus minus 3. And in this example, I have different sites. So we have, so the values that we see down below, let me just see if I can use my, I don't know if you can see my arrow here, but the first one is PCI 100, so that's one cell site. The other site is 102, 104, 202, and 204. So these are, apologize. So those are all the cell sites that are transmitting on the same frequency. Now, the bars that I'm showing there is the time difference or time offset that exists between them. And as you can see now with the limits that I have set of 3 microseconds, if it's green, is between that limit. If it's red, which is the case of the 204, that basically is above the 3 microsecond limit. And certainly that will be a problem, an interference problem between that side and the rest of them. So again, very easy and to test, but at the same time is something that we have to be careful with, that it's unique on TDD. It wasn't certainly a problem in FDD. And the other thing that we have noticed in terms of synchronization is that some of the mobile operators are changing the way in which they synchronize the cell sites. Traditionally, they were relying on GPS. So they were basically deploying a GPS antennas on every cell site. Now, the distribution of timing or synchronization to cell sites is via the network, is via the front haul or the back haul or just the network itself. And they're using basically that distribution via packets, and those packets that it's a standard that it's a precision time protocol. Basically, again, it's just packets that sending synchronization signaling into the cell sites. So that it's certainly more convenient and less expensive perhaps than GPS. However, might be subject of possible delays, impairments, and things of that nature that certainly we need to be careful with. So this is the concept of synchronization and how it might impact or might interfere between cell sites. So the next, actually, I've covered kind of the main aspects that I wanted to cover. Next, we have some additional resources where you can find some additional information. But let me just pause again to see if you have any questions.
We don't have any questions, but I do, of course. So is that the same in standalone, the timing? Is that also less than 3 microseconds in that when they move to PTP? Is it, or is it different?
No, sure it is. It's the same. The only distinction between standalone and not standalone is how the control signals are being delivered to the UE. But here we have, in either case, NSA or SA, all TDD signals, for that matter, might be subject to the synchronization problem. Let me put it this way: even if it's just data being transmitted out, in that can be NSA or SA or even a mix of them, because it's going to be possible that between two different markets, they have, in one market they have NSA and the other market will have SA. Even so, this problem might still exist because they're transmitting the control signal. It's in this frame configuration of X number of slots in downlink and Y slots in uplink, and both formats are the same. However, if you have a synchronization problem and one of them have an offset, then certainly we're going to have interference. So it's applicable for both.
Okay, thank you. And we have no other questions, so we can just move on.
Okay. So now is probably, again, I went through the material and the cases that I want to share with you a little too fast, or you might not have enough time to ask questions. But if you are interested in some additional resources where you can find more information, certainly you can do so by some of the URLs that I'm going to be showing you here on 5G overall at viavisolutions.com. Electro also, it has a lot of very valuable information about 5G. Specifically, the instrument that we've used, that it's also available at Electro is the One Advisor 800. This solution has the capability of all the different tests that I mentioned and showed during this session. And even more so, we have some how to test tips videos that you can look at. And I've created a couple of them specifically related to TDD signals and how to assess interferences and tracking modes of different interference signals. And the last piece that I'm mentioning here is for interference finding, the interference advisor, that's where you can find the information. So with that, want to thank you all. This concludes my presentation, but thank you again for the time.
Thank you, Eduardo. It was great. Just want to remind everyone that all of the slides from that we've just went through are in the handout section, so you can grab those. If for some reason you're not able to get them, just send us an email and we'll get them for you. And we'll also have a recording online later of this exact webinar. And I don't see any other questions coming in, so I think that we'll wrap it up. Thank you, Eduardo. It was great as usual.
Thank you all. Thank you, Steve.
All right, and with that, I think we'll end the webinar. Thank you, everyone, for joining.